Okay, we're continuing on with 15.6 today. We have talked about all kinds of different K values. We've talked about regular K, the equilibrium expression based on concentration. We've talked about Kp as it deals with partial pressures, acid dissociation constants, base dissociation constants, the 1 times 10 to the negative 14th autoionization of water constant. And so now today we've got one more K to talk about, and that is KSP, and it has to do with solubility. I'll give you a minute to jot that down. Okay, so KSP, the SP here stands for solubility product. And product, not actually what the product is of something that dissolves, but product as it refers to things being multiplied together in the expression for KSP. So that's where that comes from. And KSP is the study of the solubilities of insoluble ionic compounds. And those seem like contradictory statements that we're going to talk about the insoluble things and how they dissolve. But they do dissolve a little bit. You know, all those solubility rules that you guys have memorized, and all of the things that you know are always soluble, and all of the things that you know that are, we used to say always insoluble. Well, even though they're generally insoluble, there are some of those molecules that will actually dissociate and dissolve, a very tiny percentage of them. So it's kind of like how weak acids mostly stay together, but there's like a tiny percentage that dissociate. Same thing with all those insoluble ionic compounds. Most of it is going to stay insoluble, but a tiny percentage of it will dissolve. And so we're going to study that with this KSP. And the KSP expression is written the same way you write all of these other expressions, where you are basically looking at the concentration of the product to whatever power the coefficient is, multiplied by the concentration of the other product, because if it's dissolving, I'm going to have two, it's going to split up into two ions, to whatever that power would be based on the coefficient. So it's products over reactants again. The only thing here is that when we're talking about soluble, or things that are dissolving, we're starting with a solid, and we're getting two aqueous ions. This expression has aqueous only. So just like we never included solids or pure liquids in equilibrium expressions before, we still don't. So this part of the expression goes away. So it's just your products, the concentration of each product to whatever power their coefficient is in front of them. Okay, and larger KSP values just mean that they have greater solubility. So trying to find the page number where it has your chart. Page 718 gives you the chart of all the KSP values that you would just need to look up when you're doing these problems. And if you look at them, you'll notice that they're very, very small, even smaller than acid dissociation constants, because these insoluble ionic compounds, such a small percentage of them dissolve, and so that's why those KSP values are so tiny. All right, so let's just write a KSP expression. So for this one, magnesium phosphate, if I think about the dissociation of this, and this is actually an equilibrium thing because some of it will dissociate and then the ions will kind of eventually like refind each other and turn back into magnesium phosphate, and then that cycle will continue. So when this dissociates, I end up with 3 magnesium ions, 2 phosphate ions. So if I write that expression, the KSP, and again with solubility, this one's solid over here, so that's not included. It's products over reactants. The reactant is solid, so it doesn't count. These are aqueous, so those are included. I'm going to write my expression to be the concentration of magnesium ions cubed, because it's whatever the coefficient is in front of it, multiplied by the concentration of phosphate ions, and squared because of that coefficient. Okay, simple enough. We've done this tons of times already, just now applying it to dissolving compounds. All right, so let's look at some examples here. Okay, this example tells me that the solubility of copper 1 bromide, so that's CuBr, and you can just write out the equation here. This is solid. The solubility is 2 times 10 to the negative 4th molar, so that means I get 2 times 10 to the negative 4th moles per liter of this stuff is actually going to dissolve. That's not the K value, it's how much will dissolve per liter. Find KSP is what I'm looking for. So it's going to dissociate into copper ions, bromide ions. And since 2 times 10 to the negative 4 moles per liter of this stuff is going to dissolve, since I've got a 1-to-1 ratio here of everything products to reactants, that means I'm going to get 2 times 10 to the negative 4th moles per liter of this stuff, 2 times 10 to the negative 4th moles per liter of this stuff. My KSP expression is just my concentration of copper times my concentration of bromide ions, which is just this number, 2 times 10 to the negative 4th times 2 times 10 to the negative 4th, and that gives me 4 times 10 to the negative 8. That's my KSP value, and just like all other Ks, the units are pretty complicated, and so they just leave them off. You don't have to worry about units for KSP values. Okay, and KSP, I mean, it has to do with equilibrium too. So it's the value at equilibrium where you've got some of it dissociating, some of it coming back together, turning back into copper bromide, and the cycle continues. Okay, so now number 2. What is the molar solubility of silver sulfide? And it gives you the KSP value to be 1.6 times 10 to the negative 49. Silver sulfide. Silver is just one of those things you should know has a positive 1 charge. So silver sulfide would be Ag2S. It will partially dissociate into 2 silver ions and 1 sulfide ion. Now here's where it kind of looks like equilibrium a little bit, an equilibrium type of problem, because I'm given the KSP value and kind of like an ICE table where, you know, it doesn't matter how much of this I start with because it's a solid, it's not included in the equilibrium expression, so it doesn't matter how much of this I have, but I do start with 0 of this, and so that would be my initial. My change would be, and again the solid doesn't matter, so I'm not even going to worry about that. My change would be plus, and normally we would just say plus X, but you know, for some reason with KSP problems they put S to like show that it's solubility and specific to KSP stuff. So plus S there, I'm going to plus 2S, because I've got a 2 right there, here. Okay, so that gives me 2S and S. And that's my at equilibrium. So then I'm asking what's the molar solubility. Now I'm going to go ahead and write my expression for KSP is equal to, and then it's my Ag, my silver concentration squared, times my sulfide ion concentration. No exponent there because the coefficient is 1. So now if I plug in my KSP is 1.6 times 10 to the negative 49. So there's a really small number. It just means that it doesn't dissociate very much. It doesn't, not very much of this dissolves. Now my concentration of silver ions is 2S. So I'm going to do 2S. That gets squared. My concentration of sulfide ions is S. That goes in there. Okay, so my 1.6 times 10 to the negative 49 is equal to, now if I distribute all of this out, I've got to square the 2, so that gives me 4, and then that's S squared. And then times S, so it's 4S cubed is equal to 1.6 times 10 to the negative 49, which gives me my S value to be 3.4 times 10 to the negative 17, and all of these are concentrations, so it's molarity or moles per liter. And that's it, actually. When it says what is the molar solubility of silver sulfide, all it's asking you to do is to solve for S. You don't have to like re-plug it in for 2S or anything like that, because, so we'll put right here, this is our molar solubility. And what this is telling me is that I have S moles, I guess, moles per liter of my solid dissolving. That's what you're solving. When you solve for S, it's telling you how much of this solid is actually dissolving in solution per liter. And so all you have to do is solve for S when it asks you for molar solubility. All right, let's talk about, and this will be number 3, the silly hydroxides. And I'm just going to do an example to show you what I mean by the silly hydroxides. The problem with hydroxides is that, you know, a lot of them are insoluble. And so that's why they fit in with this section. But the thing about hydroxides is that there are also hydroxides, I guess I didn't need that in parentheses, hydroxides in water. So I've got these pretty much insoluble things. Some of it's dissolving, giving me hydroxide ions, but that is in addition to the hydroxide ions that are already there because of the autoionization of water. So we look at this a little bit differently. Let's look at iron 3 hydroxide. Okay, insoluble except for a very tiny percentage. The percentage that does dissolve will give me 1 iron 3 and 3 hydroxides. Okay, now solids don't matter. I start out with 0 of this. I plus S and plus 3S. So 3S and S. Now here's the problem. I don't just have whatever 3S is of hydroxide. I also have hydroxides from water. And I know from the autoionization of water that I have 1 times 10 to the negative 7 as my concentration of hydroxide ions from water. So that has to get added in there anytime you're dealing with hydroxides. And that gives me, changes things a little bit. My KSP expression is my concentration of iron, no power there because the coefficient is 1. Concentration of hydroxide ions gets cubed because of my coefficient of 3. Okay, so now if I plug in everything, and I would look up the KSP value for iron 3 hydroxide on the table or in the reference material in the back of your book. You get 4 times 10 to the negative 38 when I look up KSP for iron 3 oxide. Then for my iron 3 concentration is S. My hydroxide concentration is 3S plus 1 times 10 to the negative 7. Now, I know this is kind of like when we had really small Ka values and we could cancel out X if it was added to something. This S right here is super tiny compared to the 1 times 10 to the negative 7 even. And so if I add this super tiny number to 1 times 10 to the negative 7, I'm going to end up with, 1 times 10 to the negative 7. By the way, this should be cubed. I'm sure you already figured that out. So this is so small, and since I'm adding it to something, then I could pretend like it's not there. So that makes the math a little easier. Now, you could go through and plug in that whole thing into your solver and you would end up with the same deal. But I'd have S times 1 times 10 to the negative 7 cubed, which would give me an S equals 4.0 times 10 to the negative 17th moles per liter as the molar solubility of iron 3 oxide. Okay, now just another application of this. If you have a question that says what is the molar solubility if the pH equals 5, and it's the same kind of a deal where you've got hydroxides. If the pH is 5, then that means the pOH is equal to 9. Which means that the hydroxide ion concentration is 1 times 10 to the negative 9. And by the way, the pH would be changed because they'd be adding hydrogen ions somehow, which would lower the pH. So anyways, get my hydroxide ion concentration. Then, if I'm looking at the same problem, I would have my iron, my hydroxide, 0, 0, S, and then I would take my hydroxide ion concentration based on the pH value and plug that in, 1 times 10 to the negative 9. So then that changes my setup a little bit. I would use my KSP, which is 4 times 10 to the negative 38. Equals S times 1 times 10 to the negative 9. That gets cubed. And then you can solve for S, which would give you 4 times 10 to the negative 11, 4.0. So you should know just kind of in general that the lower the pH value, that equals greater molar solubility, meaning more of it is going to dissolve if you lower the pH. The reason why is because if, let me highlight this, I like to highlight things. If I lower the pH, that means I'm adding hydrogen ions, which will react with the hydroxide ions over here. So basically, it's kind of like taking away, this is a Le Chatelier type of question, it's like taking away hydroxide ions to react with the hydrogen. So then the equilibrium is going to shift over to the right, make more hydroxides to try and reach equilibrium again. And so since it's shifting to the right, you've got more of this that is actually dissolving and therefore greater molar solubility. common question will be, you'll be given a couple of things all mixed together, and you're going to have to decide if a precipitate is going to form or not. And so let me give you, just write this stuff down first. It has to do with, there's a calculating Q here, which is calculating values not at equilibrium, comparing to the K values, which are at equilibrium, and then determining if a precipitate will form from there. So copy that stuff down, and then we'll go through and do that example. Okay, so the question is, I'm going to have two solutions. I'm going to combine them all together, and then the question is, are you going to get a precipitate that forms? And you're going to have to go through and calculate with values that aren't at equilibrium for Q, and then compare it to the KSP value, and if QSP is greater than KSP, then yes, there will be a precipitate, meaning basically that you will have enough of what you need to precipitate. If the QSP is lower than KSP, then you're not going to have enough, so it's not going to precipitate. Now, the best thing to do, just to kind of get this, is to do an example. So I've got sodium phosphate, barium chloride. So if I write this, sodium phosphate, Na3PO4, plus barium chloride. These are both aqueous solutions. Okay, and they give me how much I have of them, what the concentration is going to be. This is a double replacement reaction. So I'm going to have NaCl, and we can forget the net ionic for right now just to kind of see the process of what's going on, plus barium phosphate. Okay, looking at this and going back to your solubility rules, you would know that sodium chloride is always soluble. So that's definitely not going to be the precipitate that we're looking for. What we want to know is do we have enough stuff of these two things to give me enough for barium phosphate to actually form. So this question is asking, will the concentration be enough to precipitate? So here's what I'm going to do. I am going to take this and I am going to write out the equation for what that looks like when it does dissolve a little bit, okay? So normally that's insoluble. It will dissolve slightly to give me a tiny percentage of barium ions, phosphate ions. aqueous. Okay, now what I need to do is I need to go through and I need to find the concentration of each one of these ions. And I need to find it from the information that's given to me up here. And they're all combined together, so I'm going to have to do M1V1 equals M2V2, plugging in, so like for barium, it's coming from barium chloride, so my M1 is 0.0025, my V1 is 50 equals M2, and then my V2 would be 100 because I'm combining two 50 milliliter solutions. So I solve for M2, which is my new concentration of barium ions, and I get 1.25 times 10 to the negative 3. And then you have to do M1V1 equals M2V2 to get your concentration of phosphate ions, which is 1.25 times 10 to the negative 4. Okay? Then I can go ahead and take those concentrations and plug them into calculate QSP. QSP is done exactly the same way that KSP is done. You're going to take the concentration of those products, and the reactant doesn't matter because it's solid, raise them to the power of whatever their coefficient is. So for barium, I've got 1.25 times 10 to the negative 3. That gets cubed because of my coefficient. Phosphate, 1.25 times 10 to the negative 4. That gets squared. So that's easy. We plug that in. Q is 3.05 times 10 to the negative 18. Now, if I actually look up the KSP value for barium phosphate, the KSP value is 6 times 10 to the negative 39. So my Q is greater, my QSP is greater than KSP. Therefore, yes, I will have a precipitate form. Okay, and I've got one more example for you. And this is, we're going to have three things all thrown together and figure out which precipitate will, or which one will precipitate first. Okay, so copy that down. We're going to have to get into the beaker a little bit for this one and see what ions we're working with and what solids we might be looking for. So jot that down and then we'll look at the beaker. Okay, I've got sodium chloride added to a 50 milliliter beaker, and that would just be like solid sodium chloride, and it wouldn't be enough to change the volume at all, so we wouldn't have to worry about that. Added to, and then they give me the concentration of lead to nitrate and silver nitrate. So these two guys are already combined together in 50 milliliters, and I'm going to add some sodium chloride to it. So what's going to precipitate first? First thing I want to look at here is what's going on inside of the beaker. I'm going to add sodium chloride that will dissociate into sodium and chloride ions, of course. And lead nitrate dissociates. Silver nitrate dissociates. Okay, now you can cross off the stuff that is under the always soluble category, because you're never going to get a precipitate with nitrates, never going to get a precipitate with sodium ions. So what I'm looking for here is basically I'm either going to get lead chloride, lead 2 chloride, or I'm going to get silver chloride. And so the question is, which one of those two things is going to precipitate first? Okay, so basically you've got to do the problem with each one. So it's easy to just set it up as a little chart and do the same process for each one and then compare. So here's what we'll do. We'll just do one at a time. Let's start with lead chloride. We'll go through that whole thing and then repeat the procedure for silver chloride. So PbCl2, and I'm going to write the reaction. If this dissolves, I'm going to get, or as it dissolves a little bit, I'll get lead ions to chloride ions. And if I think about the concentrations of each at equilibrium, again, the solids don't matter. And I start off with 0. Well, actually, I have, for lead, comes from lead nitrate, so I have 0.00015 molar of this. Chloride ions, I don't know how much of those I have, so I'm going to write 2S right there. Okay, my KSP is equal to my concentration of lead multiplied by my concentration of chloride ions squared. KSP value I would look up, or it would be given for lead 2 chloride, and I would get, and that is 1.6 times 10 to the negative 5. That is equal to, and I know my concentration of lead ions is 0.00015. Chloride ions 2S, and that gets squared. So I want to solve for S here, and S is going to give me 0.163 molar. Okay, got to do this now for silver chloride. Same exact thing. Show my dissociation here. Normally these two things, they're considered insoluble, except for a tiny, tiny bit will dissolve. So I have, from my concentration given to me up here in the problem, 0.00035. Hang on just a minute. 0.00035 molar of this, and just S over here. So looking at my KSP value, that's going to be equal to my concentration of silver ions plus my concentration of chloride ions. So KSP is 1.6 times 10 to the negative 10. That's just from looking it up in the chart. Equals, and then my silver ion concentration, 0.00035. That was given in the problem, times S. S equals 4.57 times 10 to the negative 7 molar. Okay, what these S values are telling me, S is telling me how many what the concentration of chloride ions is that I need to cause this precipitate to form. So we'll say when the chloride ion concentration equals S, the precipitate will form. So since I need less chloride ions over here to precipitate, then my silver chloride is going to precipitate first. So silver chloride will precipitate first, because it requires less of a concentration of chloride ions. Okay, let's see, your homework today is page 742, 75, 77, 79, 81, 85, 89, these aren't as long as the ones from your previous homework, 97, 101. That's pretty much all the new stuff. There's a couple things that I need to go over on Monday when we come back that we didn't finish up about indicators, so we'll do that on Monday. I'll give you guys the practice test on Monday. We will go over the practice test Wednesday, do a lab on Wednesday. Your test will be Friday. Next Friday, a week from today. Okay, have a good weekend.